Okay, so we want to discuss about what are called symplectic isomorphism in this class. So we have this veiled relation Cn, and they satisfy the following property. We know the way they satisfy this commutation relation W of alpha, W of beta equal to E power I imaginary part of alpha beta W of alpha plus beta. We know this. Suppose if we have some other family of unitaries, U alpha, which satisfy the same relation, W alpha replaced by U alpha, then they are intertwined by a unitary operator. If that is also irreducible, then they are intertwined by unitary operator. So a symplectic operator is something which gives another representation of this veiled relation. Okay, but on the same finite, with the same finite dimensional. There is this what do you want to call rank or something, this alpha coming from Cn, no, that n you can call it as the rank of the representation or something, okay, with the same index or something, whatever. Okay, so the definition, so for that it has, that also has to satisfy. See, if you apply a map from, if you have a map from S from Cn to Cn, okay, you can take any function from Cn to Cn, so that you want to talk about W of S alpha, instead of W of alpha, W of S alpha, you want to consider that should also satisfy the same veil relation. But when it satisfies that imaginary part is preserved, it will automatically imply that S is linear, real linear. Okay, and it should be irreducible. So it should be, we want it to be irreducible. So that will imply that S is invertible. And finally, it has to preserve this relation. So imaginary part should be preserved. So that is what we call it as a symplectic operator. So S is a real linear invertible operator. Invertible operator. S is real linear invertible, is said to be symplectic operator, symplectic isomorphism. Symplectic isomorphism. The definition of symplectic isomorphism, symplectic space, there is a more general version, but this is what we need for our purpose. Okay. Generally, you can have a real Hilbert space, and in G, and then on G cross G, you can define a bilinear form which is antisymmetric and satisfy some property, then work with that, and there are different purposes for that. For our purpose, this is enough. Okay. Is a symplectic isomorphism if it satisfy imaginary part of Sx, Sy. Maybe Z I should use, but that's okay. So equal to imaginary part of Xy for all Xy in Cn. Okay, Cn. Okay. So the remark is, the observation is, so as I said, W of alpha, there exists a unitary operator U from Cn to Cn, not Cn, gamma of Cn to gamma of Cn, unitary. Unitary such that U of W of alpha, U star, is equal to W of S alpha. Stone phenomenon. Stone phenomenon implies this. Due to Stone phenomenon theorem, there exists a unitary. These two representations are unitarily equivalent. But we want to fix that unitary and get that unitary precisely. Okay. So for that, I do the following. Okay. So for that, first I do prove the following proposition per notation. First, I fix a notation. Okay. So if S is a Cn to Cn, a real linear operator, real linear. Then define our notation. It's just a notation. S naught from R to N. The same thing. R to N. As defined as S naught. I mean, it is just the obvious way. You consider the real part of the inner product, but Cn is actually Cn. I mean, you are taking the actual complex inner product because you wanted to preserve the imaginary part. So you have to consider the imaginary part. Here, there is no imaginary part. I mean, here it is just the real inner product. You just take the real part of the inner product, you get the space R2N. Okay, that will be exactly equal to R2N. As a vector space, as an inner product space. So where S naught of some xy equal to real part of S of x plus iy. Okay, imaginary part of S of x plus iy, right? Okay, for x, y in Rn. If you take Rn, then you can take the tuple like this. So then you can define the S naught like this. So corresponding to a real linear operator S, you define an S naught. And given an S naught, you get the S. Okay, this is both the ways. So it's well defined association. Okay. Now the proposition. This is something we want to write that relation, that symplectic relation. Imaginary part is preserved in terms of this S naught. Okay. So S from Cn to Cn is we always when I don't say, we always consider real linear and invertible. Okay, real linear invertible is symplectic. Okay, if and only if S naught. We want to state the relation in terms of S naught. S naught star J. I will say what is J. S naught. Maybe I will say it here. Whether it is possible to. Good. And J is this operator. This is 0 identity, or I will just write 1. This is 1 is in the M cross N matrix and minus 1 N 0. Okay. This is a block matrix. Incidentally, the S naught is also given as a block matrix where each entry coming from a N cross N matrix. Okay. J equal to J. You get J. Okay. You remember there is a minus again. Okay. This is off diagonal matrix with the identity and minus identity here. Okay. So it preserves the inner product if and only this happens. This is very easy to prove. I mean, you have to notice that imaginary part of x plus iy, x1 plus iy1, x2 plus iy2 is equal to x1, y2 minus y1, x2, right? So which is equal to the inner product between them, real inner product between them. X1, x2 minus what? X1, sorry, x1, x1, y1. Yeah. X1, y1 and y2 minus x2, right? X1, y2, y1. This is the real inner product. Sorry, this is the, I want to write this, sorry. Now it's okay. This is the R2N inner product. R2N. Okay. R2N inner product. Okay. So which is same as x1, y1, j of x2, y2. Okay. You just multiply j with any j of xy is y minus x. Okay. You just multiply it to get it. So imaginary part is preserved. S is symplectic, which means the imaginary part is preserved, is equivalent to saying what? S x1 y1 J. I mean, you want to preserve the inner product. So no, this is S naught, sorry, S naught J S naught of x2 y2. Okay, this is the imaginary part of Sx, I mean S x1 plus I y1 plus x2. Let me just write it. This is equal to x1 y1 times j into x2 y2. Correct? Imaginary part of S is preserved. So that is equivalent to saying S naught satisfies this relation. Correct? I mean, something preserves the imaginary part if and only if that relation is satisfied. That is equal to that, right? That x1, y1, j, x2, y2 is equal to the inner product between x1, y1, x2, y2. That is what it means. So that's what I have written. Imaginary part of S is preserved. Okay? I have just written it in terms of real. I mean, I don't know. I just freely write the inner product. Whenever it is clear, it's the real inner product. When it is clear, I mean, okay. So this is real inner product. So now this is first term is this implies this is you can bring the S naught star there. Okay. And this is satisfied for all x1, y1. So these things clearly imply S naught star J S naught equal to J. That's all as operators. If it is satisfied in the linear functional, the inner product, okay, if two operators satisfy. Incidentally, you should remember this. This is a remark I did make in my graduate analysis course. So in a real Hilbert space, okay, X, A, Y, I mean, I'm taking the physicist inner product is equal to X, B, Y implies A equal to B. Okay. But you need this. This is not true. In complex Hilbert space, it is enough to have the quadratic form, so-called quadratic form. That is, if X, AX equal to X, BX, okay, then itself A equal to B. This is not true in real Hilbert space. Okay. So that is because of not polarity, what is called polarization identity. Okay, that's because of the polarization identity, which we don't have it in the real Hilbert space. We have something else. I mean what is it? Parallelogram identity or something else. The difference, you can write the inner product as a difference of two norm, but using that you cannot derive this. So because of this. So you have to verify that. But anyway, we have verified it. So this is the relation. So S is a symplectic operator if and only if S naught satisfies this operator with respect to J. Okay. So now we have already defined a special kind of symplectic operator. Okay. So I recall it again. Definition. Let A be a positive operator. This is in M and C. Okay. A is positive, not M and C, M and R. I'm sorry. It's a real matrix. Okay. A is positive. So you should remember in real matrix, positive means X AX is greater than or equal to 0 for all X in Rn, and A is symmetric. Okay. Symmetric means A equal to A transpose. Okay. This is true. This is in the general infinite dimension also. You can define symmetricity using inner product, and it should satisfy that condition. So it is not, if it satisfies the positivity condition in complex Hilbert spaces, it's automatically self-adjoint. Here it's not true. Okay, you need to have this symmetric. Okay, indeed, if the inner product is real, this X AX is real. That means that it is self-adjoint, and that means it's self-adjoint in the complex Hilbert space, which is not true here because here it's always real. you need to have the condition A equal to A transpose. Okay? So this is what positivity means. Okay. So given a matrix in MNC, n cross n matrix, which is positive, define SA from Cn to Cn. I have already defined it, but let me write it in terms of the zero not operator. SA naught is equal to this A00 A. A inverse is enough. I mean, this is actually, you don't need positivity. I'm sorry. Okay, for positivity, you can define positivity not needed. I mean, you can write A star inverse. Which is A inverse when A is positive. So I will erase this. You don't need positivity. But anyway, remember the definition of positivity. A is just a n cross n matrix. Then you can define star. A star inverse or A inverse star, both are same. Okay, you call this as S. So it acts on the real part as A. It acts on the imaginary part of the A inverse. This will be only real linear unless A is unitary. If A is unitary, then it will be complex linear. Otherwise, it's just a real linear operator. Okay, so this is the real linear operator. So this S naught is real linear, and it's a symplectic isomorphism. Okay, we can easily verify it preserves the imaginary part of the inner product. You can just apply the. I mean, so this is equivalent to this can. So then we can verify that J SA naught J inverse is equal to, I mean, it should be SA star inverse, which is SA itself. SA star inverse, I mean, in the R2N, if we take the star and inverse, no, it should, it should be the other way. SA star inverse. SA star inverse, which is equal to, I mean, we said we formulated the symplectic in this form, no? So this is equivalent to, you take the J S naught J inverse equal to S naught star inverse. Okay. You can take the J inverse in this side and star S naught inverse that side. Okay. So J S naught J inverse equal to S naught star inverse. So if you can verify this J SA J inverse equal to SA star inverse. Okay. It will be clear. You just multiply. Just the block diagonal matrix 1 minus 1. You can easily multiply and you can verify this. It's direct. Okay. And there is a minus. One place will become minus, and when you do the J inverse, that minus will become plus again. So this is an example of a symplectic operator. Okay. Now this is the proposition we want to prove. So slightly long proposition. I hope I will be able to prove today. So let S be from Cn to Cn be a symplectic operator. Symplectic is a property, and I say B, let S is symplectic, S be symplectic. Okay. Then there exists. So I'm making the statements on Cn. Okay, so unitary means unitary in Cn. Maybe I'll make a remark. It may split. Let's see. I expected. See, if you have a unitary in Cn, of course, it preserves the imaginary part, it preserves the inner product, so it's symplectic. But you want to, you suppose if you have only a real unitary, if you have only a real unitary, so remark, a real unitary, do not from R to N to R to N is symplectic if and only if U, the corresponding U not gives a U there, okay? U from Cn to Cn, the corresponding U from Cn to Cn is unitary, complex unitary. Okay? I don't say complex unitary because it is defined between complex. Okay. So one way is clear. This is, remark is, suppose if it is a real unitary and is also symplectic, that means it preserves the imaginary part also. It's already preserving the real part. Okay. So it becomes, so it's a complex unitary. Something preserves the complex inner product will automatically be complex linear. You can verify that. How do you verify? You just take the relation, norm of, you just write the linear combination relation. U of summation lambda I is I minus summation lambda I u is I. Take the norm square. You will expand it in terms of inner product. So it preserves the inner product, you will get answer 0. Okay. So that means if something, any function, okay, not even real linear, any function which preserves the inner product will automatically an isometry. Unitary means it has to be onto also. So it will be automatically an isometry. Okay. So now you have, if U naught is a real unitary, so it preserves the real part of the inner product. So it preserves the complex imaginary part also. So it's a unitary. Okay. You should know that if you have a complex unitary, if it preserves the real part of the inner product, then it's actually unitary because it will preserve the norm. And if it preserves the norm, it is unitary. But you have to prove it's complex linear. For that, you need it should preserve the imaginary part also. If you have just a real unitary, that then may not give you a complex unitary. Okay? Because it will preserve the norm, but it is not a complex linear map. Only if it is a complex linear map which preserves the norm will give rise to a complex unitary. Okay? So to prove that you need, it's symplectic. So it has to preserve the imaginary part, it has to preserve the real part, then it is, of course, a unitary. On the other hand, if you have a unitary, it will be symplectic and it's clear. Okay? So that's all. So this is just a remark. So if S is a symplectic, SB symplectic, then there exists unitaries. U1, U2, okay, in U of Cn, that's unitary, and A in MNC, MNR. Why am I writing C all the time? MNR, such that A is a positive operator. So if you have a symplectic map, symplectic isomorphism, then there exists unitaries in U1, U2 in Cn, a complex unitaries, and you have a positive operator A such that this S is nothing but U1, SA, U2. This is a statement on Cn, okay? And there is no uniqueness about these things, okay? We are not saying there exists U1 and U2. It's